So today's lesson is lesson 7.3, and we're going to be talking about the dot product of geometric vectors. So we've added and subtracted vectors, and we've done it in both geometric and algebraic vectors. Now we are going to multiply vectors, and there's actually two different ways of doing it. There's a dot product, which we're going to start today, and there's a cross product, which we'll do later on in chapter 7. Now the dot product we can do for geometric vectors and for algebraic vectors. Today we're going to do it for geometric vectors, and then our next lesson will be for algebraic. So the dot product is also called the scalar product, and the reason for that is when you multiply two vectors with a dot product, you get a scalar value, something without direction. Okay, so let's say take this example. Here we have two vectors AC and AB, and if we connect them tail to tail, they are separated by some angle theta. Now geometrically, if we want to calculate the dot product of these two vectors, we take the magnitude of each vector and multiply them, and then we multiply that by the cos of the angle between them. Okay, and that can lead us to a few different results. One, if theta is less than 90 degrees, so between 0 and 90 degrees, that's a positive value. Okay? However, if theta is exactly 90 degrees, well, the cos of theta is 0. So it's an interesting property that we'll talk about later in an example, where the dot product of any two perpendicular vectors will give you 0. And we can actually use that, which we'll see in an example, to show that two vectors are perpendicular. So there's lots of properties that we're going to go over, and we're going to do this little investigation to see how they work. So in our investigation, the first step is, let's say we have these two vectors, A and B. It's not labeled, but B. Okay, where the magnitude of A is 5, the magnitude of B is 8, and the angle between them is 60 degrees. So I'm going to give you a minute, and I want you to calculate the dot product of A and B using this formula that I gave you above. All right, so for number 1, A dot B, and it's really important that you use the symbol dot. That's why it's a dot product. It's going to equal the magnitude of A, which is 5, times the magnitude of B, which is 8, times the cos of the angle between them, cos of 60, and cos of 60 is just 1/2. So 5 times 8 is 40, times 1/2, you just get 20. And that is a scalar. It has no direction. You stop right there. That all depends on what the question is, right? Like these vectors, we haven't been told what their dimensions are. It just says A has a magnitude of 5. It doesn't say like 5 meters or 5 meters per second or 5 newtons or anything like that. So more theory based, really. Okay? And then we'll get into applications later. All right, so now that we've done part A, part 1, part 2 says, for the vectors given in question 1, calculate B dot A. Now this we can kind of do right now together. You can probably see if you did B dot A, you'd simply reverse these two numbers, and you do 8 times 5. That doesn't really give you a different result. 8 times 5 is the same as 5 times 8, and the cos of the angle between them is still 60 degrees. That doesn't change. So we can say that A dot B is the same as B dot A. And that I have listed up here as our commutative property. Question 3 says, for these vectors, calculate A dot A and B dot B. So I'll give you a minute, try doing that. A dot A simply equals the magnitude of A times the magnitude of A times the cos of the angle between them. But since they're the exact same vector, they're collinear. They're right on top of each other. So the angle between them is 0, and the cos of 0 is 1. So we're just left with the magnitude squared. And that property I have right up here as the magnitudes property. And that'll be true for any vector. Any vector which you take the dot product of itself, just gives you its magnitude squared. Next one is number 4. So now we're going to add this vector c here. And first, c has a magnitude of 4. We're going to find the magnitude of b plus c. So they're connected tail to tail. So let's just finish our parallelogram. We all remember how to do this. And so the vector b plus c goes straight across there. And this angle right in there would just be 180 minus 20, which would be 160 degrees. And therefore, to calculate the magnitude, we're just going to use the cosine law, where the magnitude of b plus c squared equals the magnitude of b squared, which we know is 8, so 8 squared, plus c squared, which is 4 squared, minus 2 times 8 times 4 times the cos of 160. When we do that, we get approximately 140.14. And there are a few other digits. If you want to do this investigation thoroughly, then you should just keep all the digits. Okay? And of course, that's the magnitude of b plus c squared. So if we square root both sides, we can get the magnitude of b plus c to equal the square root of this, which is approximately 11.838, and so on and so on. Okay. Part C then says to find the angle between that vector b plus c and a. So we're looking for this angle here. All right, so if we want that angle there, then it looks like I would want to figure out what this angle is here. Let's call that theta. And if I know that that's theta, then by our z pattern here, this is also theta. And then the angle between them would just be 60 plus whatever theta is. So I can use the sine law to determine what theta is. And we've done this all before. It's from chapter 6. So we would have the sine of theta all over the magnitude of c, which is 4, equals, I'll do the sine of 160 over the magnitude of b plus c, which we calculated to be 11.838. And if we rearrange to solve for theta, running out of space here, but you guys can rearrange, we'll get about 6.636 degrees. All right, so where am I going with this? The point is to analyze C and D. So now that we know the magnitude of B plus C and the angle between it and A, we can calculate their dot product. And then we can also do the same with A dot B plus A dot C. So we're trying to figure out if C and D are going to be the same. If they are, then we know that the distributive property works with the dot product. And that's our goal here. Is there a distributive property? So I'm just going to go over to the side here. If we do, I'm going to change color because I'm running out of room. A dot B plus C. That is just going to be the magnitude of A times the magnitude of B plus C times the cos of the angle between these two vectors. So A, we know is 5. B plus C, we calculated to be 11.838. And the angle between them, we calculated to be 6.636 degrees. So we get their dot product equal to approximately 23.473, and so on. All right, well, what if we calculated, I'm going to go somewhere else because I'm running out of room. What if we calculated A dot B and then added A dot C? Okay. Well, first, A dot B, we actually calculated that right here in our very first step. So that's 20. Plus A dot C, well, the magnitude of A, which is 5, times the magnitude of C, which is 4, times the angle between A and C, which we can see from this diagram is 60 plus 20, so times the cos of 80. And if we did that, you would get 23.473. So our investigation shows us that we can use the distributive property for the dot product. Okay, and there's one other property which I haven't gone over yet, and that's the associative property. That's if you have a scalar, well, we can move that scalar and multiply it by whichever vector first, and then do the dot product, or we can do the dot product and then multiply it by that scalar. It all works. The last few questions. Number 6. Here you have explain why A dot B dot C does not equal A dot B dot C. Well, let's look at this. A dot B, that gives you a scalar. And B dot C also gives you a scalar. So how could a scalar multiplied by C be the same as a scalar multiplied by A? It doesn't work. A and C are in different directions. So that's not going to work. We can't say that. All right, let's add a fourth vector, D, just because it's fun. Here's D, has a magnitude of 3, and we're going to try and explain why A dot D is the same as A dot negative D. Well, if we look at the equations, right, negative D, or the magnitude of negative D, is the same as the magnitude of D. Right? And in this case, because A and D are perpendicular, you're always going to get times the cos of 0. Even if you take negative D, it'll still be perpendicular to A. And so this is true because they're perpendicular. Right? And the cos of 90 is going to equal 0. Okay, that's not the only time the dot product can be 0. You can, of course, get a 0 for the dot product if you do a dot product with a 0 vector. Right? Like A dot a 0 vector or B dot a 0 vector. Then the magnitude of that vector is 0, and you're going to get 0. So we've talked about doing the dot product and what happens if theta is between 0 and 90, and what happens if theta is 90, but what happens if it's greater than 90? That's our first example here. This example says if two vectors A and B are unit vectors pointing in opposite directions, so let's draw that. So here's A, which has a magnitude of 1, here's B, which also has a magnitude of 1, and they're pointing in opposite directions. What's the value of A dot B? Well, if we work that out, A dot B would be the magnitude of A times the magnitude of B times the cos of the angle between them. Now their magnitudes are just 1, so you have 1 times 1, which is just 1. And the angle between them, since they're in opposite directions, is 180 degrees. Cos of 180 degrees is negative 1. So if we have an angle between 90 and 180, well, that's going to give us a negative value for the dot product. Okay, and we'll talk about how that is used in applications in a later lesson when we do applications. But mostly we're going to use the dot product to explain what work is from a physics point of view. But like I said before, you can simply think of it as, let me go back to the previous page. You're almost thinking of it as if we were to take this vector and take the cos of that angle, we're finding a component of this vector that's parallel to this vector, and then multiplying those two magnitudes. That's essentially what we're doing. And we'll look at applications later. For now, let's try question number 2. This one says, if the vectors a plus 3b and 4a minus b are perpendicular, and the magnitude of a equals twice the magnitude of b, find the angle between the vectors a and b. And it clearly says they're non-zero vectors, so we don't have to worry about that special case. All right, I'm going to do this on the side. So here's the key here. It says that these two vectors are perpendicular. Remember I said the dot product is a great way to determine if vectors are perpendicular because it equals 0. So what we know then is that these vectors, a plus 3b dot, these vectors, 4a minus b, their dot product will be 0 because we know they're perpendicular. Okay, so let's work this out. We know we can use the distributive property. So let's do that. If we multiply a through, we will have a dot that vector 4a minus b plus 3b dot that same vector 4a minus b. And that still equals 0. Okay, now let's do these separately. Again, we're distributing again. Here we're going to have 4a dot a minus, that's a b, looks like a 5, it's a b vector, minus the vector a dot b plus 3 times 4 is 12, and we have the vector b dot a, but I'm going to write it as a dot b. That's our other property, right? A dot b is the same as b dot a. And if I write it as a dot b, you can kind of see that we can essentially collect like terms there. And then lastly, 3b multiplied by minus b, using the dot product, gives us negative 3 times b dot b. And that all equals 0. Now we have some other properties here we can make use of. Here we have a dot a, and here we have b dot b. Right? Now if you remember, this is the magnitudes property. So what I can do is I can write this as 4. Now a dot a simply equals the magnitude of a squared. And I can simplify this here. Minus a dot b plus 12 will give us plus 11 a dot b. And then this is minus 3. The vector b dot itself is, again, our magnitudes property. So it's the magnitude of b squared. Okay, what else can I do? I know what the dot product equals. So this a dot b right here, I could change to the magnitude of a times the magnitude of b times the cos of the angle between them. Aha! And that's what I'm looking for. If we've kind of forgotten what I'm actually looking for in this question, it says determine the angle between a and b. And that's what that theta is going to be, because it's for the dot product a dot b. And we also know something else in the question. It says the magnitude of a is twice the magnitude of b. So I can do a little substitution here. And anytime I have magnitude of a, I can substitute 2b. So the first one, 4a squared, will give me 4 times by 2 the magnitude of b squared. Plus, here's another a. I'm going to change that to 2b. So we have the 11 out front. A changes into 2b. So I will have 2 times b, and multiplied by b again gives me b squared times cos theta. And then subtract 3 times the magnitude of b squared. Okay. So now I have 2 squared is 8 multiplied by 4 is 16. And I can actually subtract that 3 because I have 16b squared minus 3b squared. So that's 13 times the magnitude of b squared. And then 11 times 2 is plus 22 times the magnitude of b squared times the cos of theta. And we're almost done, I promise you, equals 0. Now because we know the magnitude of b, here it says they're non-zero vectors, so I know it's a non-zero. So I'm safe to divide every term by b. And so b squared I can cancel out. So now I can solve for theta. Cos theta equals, bring 13 to the other side, so I get minus 13 over 22. And so theta then equals 126 degrees. All right, so the last example says if the magnitude of x plus y equals the magnitude of x minus y, prove that the non-zero vectors x and y are perpendicular. So again, whenever you hear that in a question, you should be ringing, dot product. I can use dot product. Right? So in this case, I think I might be able to fit this question in right there. Zoom in. So here's a diagram to sort of help you see it. Now you can probably see in the diagram the only way this is going to work is if we have a rectangle. Right? If it's a parallelogram or diagonals, the lengths will not be equal. Only in our special case of a rectangle. But how do we actually prove this? All right, so let's start with this. If it's saying that these magnitudes are equal, then that's where I'm going to start. So x plus y equals x minus y. Okay, well, I can start by squaring both sides. Now essentially I'm going to use the magnitudes property, but the other way around from the previous question. So I know that this magnitude square, I can just write it as the dot product with itself. So x plus y dot x plus y. Right? So the dot product with itself gives us that magnitude squared. And I'll do the same on the other side. X minus y dot, running out of room, dot x minus y. Okay, and then distributive property again. So x and x, the dot product of x times itself, just is going to give us, again, the magnitude property, the magnitude of x squared. And then we have x dot y and y dot x, which is the same. So I can just write it as plus 2x dot y. And then y dot itself, again, gives us the magnitude. And that's going to equal, same thing, the magnitude of x squared. And here I have negative x dot y and negative y dot x. So those are the same. So I can write minus 2 x dot y. And then the magnitude, we have a double negative, so positive, the magnitude of y squared. Ran out of room. It's good I'm using different colors there. Okay, now we can cancel some stuff out because we have the magnitude of x squared on both sides. So if we subtract it from both sides, they're gone. Same thing with y. But if I add 2x dot y to both sides, they don't cancel. Instead, I would get 4x dot y equals 0. You can divide both sides by 4 and you're left with x dot y equals 0. So I've shown that the dot product between x and y is 0, and because they are non-zero vectors, I know that x must then be perpendicular to y.